Chapter 1, Section 4, Chemical Reactions. Now, with this idea that everything is made of atoms, Feynman has taken us through this journey of understanding physical processes such as evaporation and condensation, or even dissolving salt in water. In this final section of this chapter, he looks at the next thing, a different type of process. Not the physical processes as before, but the chemical ones. In those examples before, Feynman spoke about arrangements of atoms that we would call molecules. The definition of a chemical process, according to Feynman, is a situation, a process in which those atoms would reorganize themselves and the molecules would come out different than they were before. On the board behind me, I've made some notes. You can see an example that is from the Feynman lectures itself. It shows a situation where carbon atoms, a lump of coal, is being attacked by oxygen atoms. And you can see that what is happening is these oxygen atoms are carrying away the carbon atom by atom. Here, in this incomplete process, we are forming a molecule that contains one atom of oxygen and one atom of carbon. This is in fact carbon monoxide, a deadly gas that you wouldn't want to breathe. But if the combustion can occur a little bit more thoroughly, then what might happen is that carbon might get between these two oxygens, forming this carbon dioxide with one carbon and two oxygens. Now this here is combustion. It is an example of burning. And what you can see is that when these oxygen atoms get close to a carbon, they snap together. And in snapping together, they unlock some kinetic energy. And so what happens when these are close enough together that their electrons can feel the electrostatic attraction of between the oxygen and the carbon is there is a sudden pulling like magnets, which means that when they click together, they end up as a free molecule with more kinetic energy than there was before. And so some of the potential energy that was stored in the arrangement of electrons has now converted into kinetic energy. This is what we would call an exothermic reaction. That when you burn things, quite noticeably heat is given off, the temperature rises, and this is because of this snapping together of the carbon and the oxygen. Now we are familiar with this idea that the heat, as you might describe it, is due to the molecular motion of the gas, and it can be such a violent reaction that there's so much thermal energy created that some of it radiates away in the form of light. Now when this happens, we see a flame. With our new understanding of combustion, based on the picture that everything is made out of atoms, and that there is this swapping of atomic partners, the carbons are no longer joined to each other, but that oxygen comes and intervenes, well, this is really powerful. What we can do with this is make predictions that we might see not on an atomic scale, but on the scale of the everyday. Combustion is fire, and we can observe that. You see, what our atomic picture told us is that in the abundance of oxygen, what was most likely to occur was the production of carbon dioxide, one carbon and two oxygens. But that if there wasn't enough oxygen, what we would expect to see instead is the production of carbon monoxide, with one carbon being joined to one oxygen. Now, the production of carbon monoxide should really only occur in situations when the combustion is either done in a low oxygen environment, or alternatively when the combustion happens too fast. But what I've got here is, I've got a little fire. I'm going to set this burning and we'll have a little look. So right now, in the abundance of oxygen, the products of combustion here include carbon dioxide, fairly straightforward. And I have a beaker here, and what I'm going to do with this beaker is I'm going to starve the flame of oxygen, and you should watch the flame change in nature, that's just the matches going, and then die out. So very quickly that occurred. What has happened is there was no fresh oxygen, and for a split second this flame produced carbon monoxide instead. All of this we could have predicted from understanding this on an atomic scale. Feynman then takes us on to this really idyllic scene where he describes walking through a field of violets and the aroma, the smell of those violets. He describes how the odour of violet is something that is so tangible that we could actually, if we had an electron microscope, we could physically see the particle that creates the odour of violets. This is the chemistry bit, so I've obviously got to put on the lab coat. Feynman describes the odour of violets, and he draws this diagram in the Feynman lectures. You can see here is the monster that he described, a great big molecule containing a ring of carbons, but some other things, hydrogens, an oxygen atom, there bouncing around with the molecules of air, the oxygen and the nitrogen. And he describes how the structure of this was first discovered with organic chemistry. And he describes it as the best detective work that mankind has ever conducted. Because by understanding the shape of this, we were able to understand how it reacted and its properties. And you can see that this molecule here is actually displayed here with a chemical formula. And Feynman describes that all a chemical formula is a simplified picture of the molecule itself. You can see here, there is the ring, and these double lines refer to double bonds, and these single lines refer to single bonds. There is the entire structure. Now, chemistry goes to great lengths to find wonderful names for these things, and you must, of course, obey the conventions. And having asked questions about this particular molecule, I found that the jury is out about how exactly to say it. Because you can take the name and go one way round, or you could take and go the other way. But the way in which it is listed in the Feynman lectures is like this: 4-2236 tetramethyl 5 cyclohexanyl 3-butane 2-one. This is the odour of violets. And it is this that we detect with our nose when we smell some flowers. Now, that is complex, but what it means is that something like smelling flowers can be explained by understanding these molecules in terms of their atoms. So how do we know? How do we know that this is the arrangement of atoms? Well, it's a number of different ways. Scientists will form a hypothesis, and then they'll find ways of testing that hypothesis. It could be in the form of a crystal, that it's quite likely that the simple arrangement of the atoms continues on a macroscopic scale and giving a clue as to what the atomic structure must be like. It might be that we have to infer other things. We could check the shape of the molecule with an electron microscope. We could shine X-rays through the crystal lattice, and in the same way that the structure of DNA was discovered, we'd be able to infer the shape and positioning of those atoms. We can, though, directly prove the existence of atoms through things like Brownian motion. If you remember, studying of smoke or pollen through a microscope shows that jittery motion. And that in itself doesn't say much about the pollen or the smoke, but it shows that that larger molecule is being bashed by smaller molecules that we cannot see. And so therefore we can infer the existence of those molecules. And also, by examining the effect it has on that larger one, what we can say about these other molecules is we can talk about their speed, we can talk about their mass, and we can talk about their size. So there is direct observable evidence that enables us to be quite confident about the shape and arrangements of atoms in chemistry.
Right then, Schrödinger, let me read you something really important from the Feynman lectures. He says this, he says, there's nothing that living things can do that cannot be understood from the point of view that they are made out of atoms, acting according to the laws of physics. Gosh, you never work with children or animals. Thanks, Schrödinger.
Feynman concludes the chapter by marvelling on the simple fact that we are made of atoms. He says that it staggers the imagination to consider it. That he points out that though we are a pile of atoms, that we are not merely a pile of atoms.